Viewers, and welcome to another episode of Space Science with Python. Today we will finish our data engineering process with our third step called data enrichment, where we will just add some main group classifications to our data frame and then store it in some level 2 folder. It's not really a huge huge script and long video today. So it's quite easy to follow it, but after this video we are finished with our data engineering, data merging and so on. Yes, I know for our neural networks later we will need also to scale our spectra and so on, but we will do this on the fly or even in the pipeline itself. So what is it all about today? Well, let's have a look. We have here our first three scripts cells, as we also know it from last time. First, our libraries, where when we initially ask Google Colab to run it, it will warn us that it's some unauthorized script from GitHub. But yeah, I would say run anyway, because yeah, it's my script actually, and yeah, you will get probably the same warning when you open it from GitHub. Now, our second cell where we try to connect to GitHub, not GitHub, to gdrive. And it said it's already mounted. If you are also executing this cell for the first time, it will also warn you that Colab requires some access to your gdrive account and so on. And now we can read our level 1 data pickle file we created last time. So small recap, let's go here into my Google Drive, where I have this Colab folder and then asteroid taxonomy, the data, and then level 0 and level 1, and level 1 contains the pickle file from all the raw data that are stored in level 0. And today we will create our level 2 folder, which is then the fundament or the basis for our future analysis and visualizations. So what are we gonna do today? First, let's have a look at our classification from last time. Before we take this look into this picture, I created some small markdown cell. This is what I like about Jupyter Notebooks. Jupyter Notebooks are not really sufficient, let's say, or good to use them in a productive environment. I would always suggest to create actual Python library or Python scripts and not this Jupyter Notebook. Jupyter Notebook tend to be chaotic if you are having or creating huge projects, so be aware of this. But it's quite nice to add markdown recipes or stuff like this to enrich the Python scripts a little bit with scientific content. So I found this nice article from 2019 where it says, well, it's an article about the history of the asteroid classification. And I have to say, this is a very nice article that summarizes all the classification schemas we discussed last time and also the time before, where we have here the taxonomy described, this C class, S class, U class, and so on. The author also created a huge Sankey diagram with all classification schemas. So this is really, really huge. You see all the publications from 1975 to 2013 with all the classifications of the asteroid data, of the asteroid spectra. And here on the very right side, you see we have the main groups, the S, the X, and the C class. And here it's called end members and outliers. We will just call them other or others. Of course, we will not now encode all classes. We have our Bus et al. Classification schema, which is here, I think. Yeah, it's Bus. And then we will add now the main group classifications to the data frame. And why are we going to do this? Well, we will need to see some statistics, whether we have enough Bus classification asteroids for our training. So for example, if you have, let's take an example, a T asteroid, we have only like 3 spectra. Well, for a classification algorithm, this would be totally insufficient, and then mapping this to a more generic or huge or summarizing class would be more beneficial for some kind of classification algorithm. So yeah, we will just, later we will create algorithms for the bus classification as well as for the, let's call them main groups. Now, if we go back here, we have some very nice explanations also regarding the reflectance spectra and the different properties of the asteroids. So I really encourage you to do this. You see here also by Bus and Bus Demeo the different reflectance spectra. Yeah, so for example, by the different classes. So let's take, for example, this one here, where we see on the y-axis the average spectral slope is increasing, so it gets steeper and steeper. And you see here then the different classification classes like D, T, X, XE, and so on. You see it becomes flatter and flatter, and also some other weird spectra, O, Q, and so on. And you see that the absorption lines and so on, as they describe it here in different absorption bands, depend or are coupled to some kind of, or to the abundance of minerals. So the minerals on the surface, they cause this reflectance or absorption at certain wavelengths, and this is the reason why we have so many different classes. And yeah, we will also see later whether we have also some kind of transition regions between T and X and so on. But before we tackle this, I would suggest to just simply map the main group classes to the class we already have in our level 1 data. Enough of speaking. Yeah, I would suggest, did I execute the third cell? No, let's load also the data from level 1. And now let's add the, let's map the main groups to the bus classification. And the lazy person that I am, I already created. Oh, I didn't create it. Oh, this is awkward. I thought I created it, but yeah, I didn't create it. So let me just switch quickly back, and I will be back in a moment where I will show you the classifications. And actually, I had this the data here in Atom Editor, but I somehow did an undo, so it was gone. Let's copy paste a simple dictionary where we are mapping the bus classification to the main group. So we see here A goes to other, B to C, C to C, CB to C, and so on and so forth. And this dictionary is hard-coded by myself using this Sankey diagram I showed you just a moment ago. So let's execute this cell so that Colab knows that we have this dictionary with the mapping, and now we can simply map it or add our new column to our data frame, where we just say asteroid df.log. So we create our main group classification. We simply call it main group, and we use the asteroids df. The bus class, so let's write bus. I think it was an underscore, right? Yeah, bus class bus underscore class, and then we apply the lambda x and say that this bus to main dictionary needs to be applied, and we will say get x, and just in case we missed something, we will replace it with none, but I don't think there is anything missing. So Shift Enter, and we execute it and create our next cell. So let's take a look at this asteroid DF we have now. So this is now our data frame. This is our main group. We can simply check main group. Yeah, we execute it, and we have only this this column, and then we say unique, and then we say C. Okay, we have C, S, other, and X. So we mapped all bus et al. Classes to the main group. So the none is not here. So this looks quite nice. And now I see here I just crossed the vertical limit. Okay, And now we should also clean up our data frame a little bit to keep it clean and tidy. And we can remove, for example, the designation number, I would say, and also the file path, so that we have like the series, so the name, the designation number with the name, the bus class, the spectrum, and the main group. So yeah, let's stick with asteroids df and let's drop 2 columns. We use the drop function where we say drop columns equal, and then we provide a list with the name, with the column names that need to be removed. So we say designation number and file path. And since we are not addressing this to a new data frame, we have to say also in place equals true. So it will automatically replace asteroids df with our new data frame that is simply a copy of asteroids df, but with removed columns. We have here now, we have now the name, bus class, spectrum, and the main group. Okay, so just small reminder, if you would like to start plotting these things, feel free to do it. We will do this also next time, plotting some spectra in a very interactive, and I hope for you also fancy, interesting way. We can take a look, for example, at series. Yeah, series, and then we say spectrum df. So this is like, the spectrum that's here is a data frame in a data frame. So we take the 0 and we have here our data frame. And just a small reminder, we have a column with the wavelength in micrometers and the reflectance normalized at 550 nanometers. So here 0.55 corresponds to 550 nanometers, which is like, I don't know, maybe some blue or green light, and we have here the reflectance of 1, and then the reflectance whether it's now whether it corresponds to a weaker or stronger reflectance, it corresponds into this normalized values. And if you compare it, for example, here, let's take a look. We have here 0.44 with a number smaller than 1, and here we have something at the end, values larger than 1. So we have a slope which goes from some we have some positive slope probably. We see we have here a lot of different spectra of this positive slope, and we can also take a look at series. What is series actually? Is it we can take a look here. It's a C class, so in the main group also C. We can switch back and see, the C classes, they have some kind of positive slope. So this actually makes sense. Again, feel free to use now Matplotlib, for example, to plot these data from Matplotlib. Import pyplot as plt. I don't know if Colab has Matplotlib. Yep, it has. So we can simply create a figure. I will not provide this now I will not provide it in the script, but just for you to get a feeling on or understanding how to do it. We say plt plot and asteroids df. Let's take series, for example. So we take this command here. So quite huge. Here is X, this is Y, and the column names are, just copy paste, the wavelength in microns. So like this. And the other one was reflectance normalized, but I don't know how I wrote it. Okay, reflectance norm 550 nanometers like this. Okay, it exceeds the vertical line, but doesn't matter now. Let's see whether this works. Yeah, and you see here now the spectrum of series, with this positive slope. And you see the resolution is not very high. Just a reminder, we have a resolution of 10 nanometers. So each data point corresponds to 10 nanometers. Here we have the micrometers. Here we have the reflectance. So this gives you a small idea how a spectrum looks like. But next time we will create an interactive plot with widgets and so on, where you can really play around in your markdown cell with different spectra. I think you will like it. So Let's do it next time, but yeah, we should also store our data frame, so that otherwise we did it and we have to redo it next time. So we are creating again a new level directory. I call it level 2. I mean, this is a small new data frame. Level 2, create a parent if they're not there, but they should be there. Parents equals true. And exists equals true. And then we can store our Asteroid df file as a pickle file as before. So quite nice. OS path join core path. Now before I finish the script, you see I repeat the cells a little bit, right? And this is what I say, that Jupyter Notebooks shouldn't be used for productive environment. We have here code snippets that are a little bit redundant, like reading in the or mounting the gdrive, or also storing data in gdrive. This could be put into some functions and later into some classes. Fully agree if you already have this thought. Here in this tutorial, I will just rewrite it all the time, you know, also for you to get familiar with the commands. But if you are planning to create a larger project or so, I highly encourage you to put redundant or repetitive functionalities into actual functions. And if you have a lot of functions, then maybe it would be worth to create a small library that suits your needs. And with a library, you can also do some testing, unit testing, and so on. I highly encourage you to do this. So here it's for a tutorial, it's fine, but in fact, it's you should be aware that it's not best practice. So let's store it as an asteroids PLK, and then we can simply store it. I'm executing it here. And let's take a look into Colab. Into gdrive, we have here level 0, level 1. Let's refresh it. We have here level 2 now. Perfect. So let's go in there. And there's our Asteroids PLK. Very nice. So we are now prepared. So we have everything in place in gdrive. We have everything we need now for our next task. So as a small summary, what did we do in the last videos? We downloaded the data, we merged the data, we cleaned it a little bit, and we created higher level data products that can now be used for data visualization, for machine learning, and so on. What is the next task? So what is the outlook for next time? Next time we will create an interactive plotting routine where we will get a better understanding and feeling of the C asteroids, X asteroids, and so on. Because instead of directly starting with some ML algorithm, it's always important to understand the data, to have a look at least at the data, right? So if you, for example, have some pictures of dogs and cats and you want to build a classifier, you will for sure plot at least a few pictures to see, okay, are there actually dogs in there and cats? How do the pictures look like? Are the dogs maybe only huskies or so? Of course, based on some examples, you cannot derive general rules for the entire data set, but having some kind of feeling is really important when you are conducting machine learning experiments. So be always aware to take some time for exploration, for simple statistics and so on. It's not a shame or whatsoever. Yeah, some people say they want to start immediately with some deep learning. Always step back a little bit and check the data, because it saves you a lot of pain. Especially to the students here, if you're creating bachelor thesis, a master thesis, or working on your PhD, don't have the urge to create something quickly to impress your supervisor or whoever, right? Be more sustainable, check what's in the data. So you are really 100% sure what's in there, and then you have a fundament you can rely on for all your machine learning projects that are coming. Yeah, so you don't have to rerun everything, recheck everything. You can be 100% sure, okay, let's say 99% sure that you did proper work. Okay, I hope you liked the video. Again, small, simple scripts, no magic involved. Next time we will create our visualization routines, and then afterwards we start with some analytics. I hope you're looking forward to it. I already do. And until then, see you next time.